Right, so let's have a look at a fair and honest voting system. Okay, so let's say we wanted to create a voting system. So it might be for a local election or maybe for a national election, and we want it to be fair and honest so that we can vote electronically. So in this case, Bob, Alice and Eve can vote, but the votes that they cast can be anonymous. So they can register their vote and it can be seen that they've actually voted, but it won't be possible to tell what they've actually voted for. And then what we really want also is that the results of the voting will be automatically released to each of the citizens without actually revealing any information about how the other voters have voted. So in this way, we don't really need Trent anymore, but Trent could collect and register the voters and make sure that the voters are acceptable and that they cast their votes on time. The method we're going to look at is based on this paper. So it's anonymous voting by two-round public discussion. It's a two-round process where citizens will register for a vote and then they will be able to cast their vote anonymously. If you're interested, the paper is here, and I'll just show you what the paper looks like here. So a further paper continued this on, a recent paper continued the work on to look at blockchain methods, integration of blockchain methods. So this is the paper here. Okay, and if you're interested, here is the methodology that's used. So I'll go around the basics of it and I'll show you some code to actually implement it. If you're interested in the details, please ask on anything that you're unsure about. And the basics of it are to use discrete logarithms. So the discrete logarithms are in this form here. Okay, so we have a g, a generator value, and then we have a value of x, which is our secret, and then a prime number p. So we calculate values y is equal to g to the power of x mod p. That's a log type function. And the log base that we're using here is g. So there are values of g. We'll pick a value of g, and in this example we'll pick a value of 2. And there are safe values of g for the prime number or the value of p that we actually pick. What we really want to make sure is that for every value of x less than p, we'll generate a different value of y. So some g values won't work, so we pick a safe one from them. Okay, so in the code that I'm going to use g equals 2 and p equal to 67. So I've selected very small numbers. Obviously we wouldn't use that small a number, just to really illustrate and to keep things nice and simple. Okay, so that's discrete logarithms, and the challenge of discrete logarithms is it's very difficult to find the value of x, even though you know p and g and y. It's almost impossible to find out what the value of x is because there are so many different values that could have caused it. Okay, so let's look at that. So if you're interested, here is the link that shows how we can pick a value for g, and I've got a little demonstration here too that you can have a look at. Okay, so for a certain prime number, so I'm going to pick 67. So for 67 I can use 2, 7, 11 and so on for the value of g. That's my generator value. So the code is here if you're interested. There's the Python code. But we just need to make sure that for our prime number and our generator, for each value of x up to p, we generate a different x value. You can see it works there, but it doesn't work. It doesn't work here because we can see it repeats them. So 4 isn't possible of a generator value for a prime number of 11, but 2 actually is. 2 is quite common and picking a value of g for something like Diffie-Hellman. So that's for selecting that value then. Okay, so I'll show you the code in a little minute. Sometimes it's easier to look at the code before you look at the basic methodology, but we'll have a look at how it's all set up. Okay, so in my example, I've got 5 voters, so that's the value of I, and then each voter will create a value of a random value ix. Okay, so Bob will create his ix value, and Alice and Eve, and so on. This is a secret value and shouldn't be given away to anybody. What happens next is that each of the voters will give a value of g, our generator value, to the power of xi. Okay, and that's going to be used as their main identifier for their vote. They then give what's called a zero knowledge proof that they know the value of xi to Trent. So let's say Trent is managing the election. So each of the voters will raise g to the power of x, the random number. But because it's discrete logarithms, we then bring in a mod of p. Okay, if you're using Python, then it's a percentage p. So each voter passes g, our generator 2 in this case that we've selected, to the power of the random number, and then mod p. So I'm going to use a prime number of 67 there. I'm going to use a generator of 2. Okay, so those values are there. The zero knowledge proof is then used to show that each of the voters can actually prove that they know the value of xi without actually revealing it. So there's been no passing of the random number. All we've done is that we've sent these values, these discrete logarithms, to Trent. So now each of the voters will see all of these values, and then we'll regenerate these keys here. Okay, the paper explains it fairly well. This is the multiplication symbol. So this is g to the power of x1, g to the power of x2, and so on. Okay, so that's what the multiplication. In logs, if you know logs, that's equivalent to x1 plus x2. Okay, so basically what we're doing there is we're summing the values of the votes. And this is a divide here, so we don't include our own value when we're calculating these ones. So this is a divide, and a divide is similar to a takeaway. So if it's x1 divided by x2, that's equivalent to g to the power of x1 minus x2. And there's a really good explanation of this in the paper, really quite a great explanation with a little table that actually shows how the values are added and deleted, and how you will end up cancelling the values out. Okay, so I hope this makes sense. I'll show it in code in a little minute, but this is a divide. We go through some sort of loop here, and we do our multiplication, and then we get to a certain point, and then we'll divide by numbers after our own value. Okay, so that's the values that we have in there. So after this, each of the voters will then take the value they've calculated. So let's just rub that out, and we'll start to work on the next part. I hope you understood the bit about the divide. It's a kind of weird, it's one of the laws of discrete logarithms about the adding and the multiplying becoming adding, and then the dividing become taking away. So the next part we've got is this part here. So each of the voters has calculated that value. So that now they must calculate g to the power of xi, g to the power of yi, and then they'll take their vote and they'll add on here. So if it's a yes, they'll add a 1. If it's a no, they'll add a 0. So this becomes a 0. So we take g to the power of 1 or g to the power of 0. This one here, xi, so we obviously know g to the power, we obviously know xi, and we've just calculated g to the power of yi. So how do we do this next bit? Well, if you know anything about logs, then a to the power of b actually becomes a to the power of b to the power of a. That's just a rule of logs. So what we have here is that we take g to the power of yi, which we've just calculated, and we'll raise that to the power of xi, and then we'll multiply that by g to the power of vi. Okay, so we know that because we've just calculated it there. We know our own xi, so we can actually calculate that too, and then we'll add that, we'll multiply that to our own vote, and then this becomes our vote. So our vote is then published to Trent, and everyone will be able to see the vote but won't be able to determine what we've actually voted. Okay, so on the next part, what happens is that all of the participants will see all of the votes cast, and then they will be able to multiply them all together. As we said, this is the multiplier. It's just like what we said before, when we multiply we're actually adding, and because of the way that we've done this, then we cancel out, and that this part cancels out, and we end up with a summation here. So we have g to the summation of all the votes that were cast. So all we have to do now is do a discrete logarithm, or we can do a search if it's a very large value. So we can do an inverse log of g of vi, and we'll determine what the number of votes cast are. Okay, so that's the basic methodology. It probably takes a while to really let it sink in, but it's really an interesting method that's been used here. So let's now look at the coding for this. So I've coded it in Python just to make it nice and simple. I've used some simple values, as I said, g of 2 and p of 67, just to keep it simple. Okay, so we'll go through an example first. So let's say there are 2 yes votes. So each time we'll generate random values, and then what we'll do is these are the g to the power of the random value mod p. Each participant will calculate, for each participant they will calculate these y values, and then each participant will make their vote, and they can only make the vote because they know their vote and they know that the random value, and then we'll get the tally here. So hopefully this will give us 2. That's correct. Now let's have 3 yeses, and that's fine. So it shouldn't be possible to look at the values here and to determine who's voted what. So if we look at the code, so the code is here. Okay, so we'll just take you through, this is just setting up an array of votes here. And then we'll set up some random numbers. I've just used 1 to 30 as a random number, but obviously these would be large, typically 256-bit random numbers or even greater. What we then do is we then publicize each of the voter registrations as g to the power of those random values, and then again we could do the mod p. So I've just set up a static g and p there. So after that, what we'll do is we'll go round, and we also set a zero knowledge proof to Trent to show that we know what the value of xi is. If you're interested, I've got a few examples of that. Then we do this multiplication and then this divide. So if you go back here, this was this equation here. And what we're doing is that we're going around the loop up to I minus 1. Remember in Python, it goes up to that one, but one less. So then it calculates the value, start with 1, and we go around and multiply each time, which is the same as adding of the values together. And then for the divide, what we've got to do is the inverse. So when we do a divide, we get the inverse of the value. So we're taking the value and mod p, and we do an inverse of it, and we multiply our value with the inverse of p. Okay, so this is how we do divides in discrete logarithms. After that, we'll publish our public values there. Just print them, print the values of y that we've determined, and then we're going to create the votes. So the vote was the y value to the power of the y value there. The y value to the power of xi. That's the voter value there, and then it's times g to the power of the vote, as we saw. So if we go back, that was that equation here. Okay, so that equation, we know what g to the power of y is, which is that we raise it to the power of the voter, which was the xi, that was the random value, and then we multiply it by g to the power of vi, which is the vote that we're going to have, and we obviously take mod p each time. Okay, so that's our result, is then the multiplication of all the votes, and mod p again. Okay, if we go back to our equation here, so this equation here is what we're doing here. So that will give us a result here, and then what we've got to do is the inverse log. Okay, so we'll just take the log. The one way we can do log to the base g is we take the log of the value and then divide it by the log of g, and it'll give us the result. Okay, so there's some examples there that we get from the result. Okay, so I hope that makes some sense. It's a bit strange initially when you come across this type of operation, but it's increasingly used in things like blockchain, elliptic curve methods, a lot of zero knowledge proof things are now analysing this type of thing. So I just summarise a little bit on that basic principle of when we have something like g to the x1, g to the x2, and that becomes g to the x1 plus x2. Okay, and that really what's going on here. And then this principle of one value and another value, that is equivalent to that. Okay, and that's what we did here. Okay, and I think the other one that we looked at was something like this, where we were dividing, and in logs, as was discovered by John Napier, that is equivalent to that. Okay, and if we just look at the paper again, actually I'll show you the basic description of that, that little grid that is shown. That actually shows how things actually get cancelled. This one here is just showing you for an example of n equals 5, that the pluses and the minuses all cancel out, and we'll end up that this part here gives us g to the power of the summation of the vote tally. Okay, for larger vote sizes, you can use these types of, you can do an exhaustive search for the values, or you can use this Shanks baby step, giant step algorithm. Okay, so that's covered some open and trusted voting.